Hello ladies and gentlemen, welcome back to what is essentially the 9th lecture of GGS300, so Quantitative Methods for Spatial Science. Today what we're going to be going over is two sample tests. So just before we begin, I just want to give a little bit of an update as to where we are within the course. So we're in the second part, the second third now. We've got a couple of lectures left now until the next midterm. There is an assignment that's going to be set today, and that's going to be due on April the 1st. So you've got the standard 7 days to complete that. I've actually really been enjoying speaking to some of you in greater detail since I basically reached out to all of you last week just to kind of catch up now that we've had quite a substantial amount of the work set and you've handed it in, it's been marked and you've got your midterm results. Some of you are doing very well. That's great. If you still have room that you want to catch up on, then you've got plenty of time to do it. And don't hesitate to reach out to me if you have any further queries or issues that you want solving. I think the astute among you have figured out that if you have queries, it's better just to email Ed and get a reasonably quick response from me, particularly to provide guidance for things like the assessments. So make sure you look at this assessment early. And anything that you're stuck on, don't hesitate to ask me, and hopefully that will provide you with the right kind of guidance that you need to really excel at this course. So today we're going to be focusing on a further development from the work that we did last week. So last week we were focusing on hypothesis testing, and we were focusing on single samples that we've collected, whereas this week we're actually going to be focusing on collecting two samples, so trying to understand whether those samples are from the same population, and then actually looking as well at different types of sample tests. So we'll be doing both the standard mean sampling approach as well as the proportional approach, and then covering both parametric, so normally distributed data, normally and non-normally distributed data, so non-parametric data, inferential tests. Okay, so that's enough from me. Let's get stuck into the main kind of content. So the first third of the course we were over here, and this second third of the course we've moved over here into the more inferential statistics part. And I'm not going to spend too much time going over this again. One of the things that I did want to introduce to you, because I don't think I've done it yet, is the idea that it can be quite challenging, as I explained previously, to actually work out which test you should use. And I've been in your shoes, and I've been really quite overwhelmed by the number of tests that there are, and feeling like I didn't really know which the right test was to choose for my particular research problem. Okay, and that's why I just wanted to kind of introduce this idea that there are plenty of very good resources out there which use flowcharts. Okay. And the beauty of this is that you can kind of have a think about the data that you've got, and you can have a think about some of those characteristics that we've covered many times before within this actual class. And essentially you can kind of work your way through this flowchart in order to work out which specific test is probably right for you. So if you've got discrete categorical data, we'll cover this later in the semester, you might go over here and use the chi-squared test, for example. But generally, as we'll be covering today, you'll probably have continuous data, in which case then you need to think about the type of question that you might be asking. So if you're thinking about relationships, then this is stuff which we'll be doing in future weeks, so particularly regression analysis, thinking about correlations. Or if you're thinking about differences, which is what we've been doing the last couple of weeks, then you'll be over here, particularly if you're working with means, as we are today, and particularly if you're working with different groups, and here we're working with two groups today. So when you follow this flowchart through, you end up down here. And essentially what we need to decide then is how our data are actually distributed. So are they normally distributed data, which we've covered in the previous sessions, so that means that the data conform to that bell-shaped Gaussian curve that we covered. In which case, if that's the case, then you'll be able to use either the unpaired student's t-test, just known as a t-test in many cases, or the paired t-test. So this is for where you don't have independent samples. We'll be covering this today. Or if you have non-parametric data, so for example, if those data distributions that you have do not conform to that Gaussian distribution, and you might even test it. So I mentioned before that we will be able to use later in the term a Kolmogorov-Smirnov test, which indicates whether your data are normally distributed or not. If that came back significant, indicating that your data aren't normally distributed, then you'd think about a non-parametric approach to testing these two different means. So you could try a data transformation to try and transform it into normally distributed data, and if that doesn't work, then you'd end up looking at the Mann-Whitney U or the Wilcoxon rank sum test. So these are pretty much what we're going to cover today, with a few additional tests thrown in around the edges. Don't forget, if you're struggling, well, not if you're struggling, but you should follow the book and read this chapter for this week, and particularly if you're struggling with this content and the lab, make sure you read back over the parts of the book that are highly relevant to the particular problems that we'll be covering in this week. So what we're going to be looking at is chapter 10 here. So this covers two sample, dependent sample, matched pairs difference tests. Okay. So what are we going to cover today? Well, as I mentioned, we'll be focusing on both those examples where the samples are independent and those where they're not, so they're dependent and they're matched pairs. And don't worry about all of this terminology, I'll go over it all today, so you've got plenty of time to adapt to what I'm talking about. But I think the key point is that, as I've already mentioned, we have these broken down based on whether they are parametric, so normally distributed, or non-parametric, so not normally distributed. So what we're going to cover is, for independent samples, the parametric side will be covering two sample difference of means and two sample difference of proportions tests. And then if your data are non-parametric, you can alternatively use the Wilcoxon rank sum test. So the way that we approach it this week is that we actually just convert some of the existing data that we use for the parametric test to ordinal data, and then use that in the non-parametric test approach. So you'll be able to compare both sets of data that we analyse, and you'll be able to look at that within the book. So there's quite an extensive example within the book which goes over those different tests. And then if your data aren't independent, so I'll explain more about this later. If they're dependent, then you need a matched pairs test. In which case you can use, if the data is parametric, you can use the matched pairs t-test, or if it's non-parametric, you can use the Wilcoxon matched pairs signed ranks test. Okay, so there's a lot there. I don't want to overwhelm you with it, but we're going to work through this incrementally now, and I'll definitely go into some of those terms which I just used to describe what an independent sample is, and I'm going to give you examples so you really kind of get the hang of what I'm talking about when I talk about these different kind of samples, and hopefully that will cement the ideas that we cover here. So as ever, this is going to be relatively high level. It's going to focus on the math that you need to cover to understand these tests. It's not too hard. So hopefully you'll be able to pick that up. But obviously this is more kind of high level. It focuses on the assumptions required and some of the theory. And then we're going to get into the nitty gritty in the actual lab practical, where we work through these tests and then actually look at how we crunch the numbers within the R environment. Okay, great. So without much further ado, I'll move on. And essentially, these are some of the concepts that we first need to consider if we're interested in testing two different samples. So as I mentioned before, in the previous lecture, we were focusing on just a single sample test. So we went out and we collected data, and I think I tasked you with collecting house price data in Fairfax and comparing it to Virginia at the state level, so that was the population. And then I was wanting to understand whether that data might be different or basically from the same population. And as a consequence, we did a variety of hypothesis tests and with the 6 steps that we went through, and then at the end we introduced the idea of significance testing as a shorter way to kind of circumvent those 6 steps once you have the hang of it. The point is, therefore, is that now we're focusing on those 2 different samples, and that means that we're going to be seeing whether they're drawn from the same population or whether they're drawn from different populations. Okay. So there's examples here. My favourite one that I'll always go back to is testing if the house prices change, maybe in relation to some sort of economic disruption such as COVID or the global financial crisis that we saw in 2007, 2008. So maybe when we have two samples here, we're referring to I make you go out and I make you collect house prices for Fairfax, Virginia. That's nice and easy. And then I also send you to Richmond and ask you to collect house price data there. And then we're interested in whether they come from the same population or not. There's lots of other examples. We could test if cities have different crime rates. We could test if forests have different mean tree heights. We could test if production on agricultural in agricultural areas increases after they introduce new management practices, and so on and so forth. The question is whether the samples are significantly different, and then if they are, then we can conclude that the samples were drawn from significantly different populations. And then if they're not significantly different, we can conclude that the samples were basically drawn from the same population. So this is kind of the driving force for how we use these tests. You kind of need to think of it in these terms, so write it down and learn it. This is kind of the logic for why we're testing in this particular way. Data type is important. So for the one sample tests, we had different tests depending on what type of point statistic we were using, whether that was the mean or whether that was the proportion. This still occurs in the same tests which we're going to cover today. The only difference is that today we're also going to be introducing those other types of data forms which maybe we didn't cover in the previous classes. So we covered parametric approaches in the previous classes where we have interval ratio data. We're focusing on the mean in relation to the normal distribution. But what we're also going to be looking at today is when we basically have nominal, so remember that's categorical, or ordinal, remember that's categories which have an inherent hierarchical order. And basically these will form part of our non-parametric based approach. Okay, so I explained before that what we basically do in these examples today is we downgrade our parametric data to be non-parametric, which is a perfectly acceptable way to approach the problem. Ideally though, in reality, you'd rather have parametric tests because they're much stronger than the non-parametric versions, but this is kind of a fallback if the data that you've collected don't conform to those assumptions that are required for the parametric version. Independence, I'm going to keep coming back to this because it's a really key thing, not just in what we're doing today, but also when we get to regression analysis later in the term. And for geographers, spatial scientists, this idea of independence in statistical tests is a really, really tricky issue and something which is going to keep coming up because geographic data isn't always independent, and therefore you need to be very careful with how you design statistical analyses around this because you might breach that independence assumption required. And if not, then you need to actually correct for the lack of independence using things like geographically weighted regression, for example, these other forms of spatial statistical testing, which are specifically there to try and control for this lack of independence in some of your input data, which basically can happen across space when you're using artificial spatial boundaries. Okay, so I think we covered this in the previous parts of this course. So we probably covered things such as spatial autocorrelation, which is a classic independence issue because it means that your data points aren't independent, they're autocorrelated across space, which means you breach this assumption. So in this particular case, we're going to be focusing on the first set of tests, assuming that the samples are independent. So this is where those samples are unrelated. So this is, if I sent you out to sample Fairfax and I sent you out to sample Richmond, these are not in any way related. They're different, completely different places, very, very far away geographically. And therefore, it's a fairly acceptable assumption to assume that those samples are independent because it's truth. The difference is that in some cases you might not be able to meet this particular assumption. So if we went and I asked you to sample house prices in Fairfax, let's say I asked you last year, and now I'm asking you to do it again after COVID, I want to know whether that's had any impact. So if you're taking two samples in Fairfax, then they're not independent samples, they're dependent, that it's the same area, it's the same properties that are being sampled again, and therefore you just need to use a different approach to actually developing a statistical analysis using that data. So when we say matched pair, that means the same entities are being sampled, in this case, twice. Okay, so it's very good for kind of testing an intervention and seeing whether that intervention has actually worked or not. And then I just make the point at the bottom that independence of data is a perennial issue in the spatial sciences. Yes, I think that's a good way to put it. Okay, so a couple more points before we move on. There is only one two-sample test of proportions that we're going to use here. Independence does not matter for proportions, but it is very important for means. Okay, fine. I mentioned before that the same hypothesis testing approach is fairly central to these two-sample testing approaches, but actually we're also going to use the p-value essentially to circumvent all of those steps now that we kind of actually understand that concept really thoroughly. Okay. Great, let's move on and let's start to get into the first set of tests that we want to explore. So these tests are designed to check if those different samples that we've collected are taken from the same population or whether they're taken from different populations. We do need to assume that those data samples are independent of each other, and choosing geographically separate entities is a very good way to do that. So the way that dependence works is that if you measure by distance, it goes back to Tobler's first law of geography. So things that are together are more similar, things that are further away are less similar, essentially. Okay, so this is kind of the way to think about it. If you're choosing entities which are very far away from each other, hundreds of miles, hundreds of kilometers, then you would be pretty confident that they're fully independent. Okay. So the parametric tests that we're going to cover, I've already mentioned, are the difference of means and the difference of proportions to sample tests. And then for the non-parametric based approach, we'll be focusing on this Wilcoxon rank sum test, which sounds really weird. But remember that all of these tests are named after the people who basically came up with them, right? And that's why they have all of these funky names. But we'll cover more of this later in the course, and also I'll go over exactly what all of these are in the lab so you can understand how to calculate them. So let's get stuck in now to the very first test, and obviously here we're comparing the means of those two independent samples that we're collecting to see whether they're from potentially the same population, or if they're significantly different, then it would indicate that they're from different populations. Okay. But there are assumptions that we need to meet, and in the book these are always called requirements. I think of these as assumptions, but essentially we need to have independence in the samples, fine, and then we need to have the populations actually being normally distributed. So Gaussian, well, that's understandable because we are using parametric based tests here, so they have to meet that normal distribution requirement. And we need continuous data, okay? So I mentioned before, this is just for interval or ratio data, so we can't use ordinal or categorical data here. The hypothesis, well, that's fairly straightforward. So the null is that the mean of the first sample and the mean of the second sample are equal to each other. Whereas for the alternative hypothesis, you would indicate that you would not expect them to be similar, they would be significantly different, essentially. And this could be two-tailed, so you don't specify which way the actual direction of the effect runs. You're not saying whether it's higher or lower, you're just saying they're different. Or you could use a directional hypothesis here, where we're saying that the mean of the first sample is significantly lower than the second sample, or the alternative down here is that the mean of the first sample is significantly higher than the second sample, okay? Great, and then the actual test statistic of interest depends on the test that you're using. You could use the Z-score or the t-test depending on your sample size. For this week, just for ease, what we're actually doing is we're focusing only on using t-tests, so samples which are below 30 in the number of data points which we have, and we're only focusing on the separate variance estimates. So this is just a statistical term which you don't need to worry right now, but we're not getting into more complicated pooled variance estimates, okay? So what we want to do essentially this week is calculate the t-value for the data that we have. And the way to do that is you need to get the mean of the first sample and subtract the mean of the second sample. So this is the difference between the two samples that we have. And then we need to divide it by the standard error of the difference between the means. Okay, so this sigma value here, which is the standard error of the difference between the means, can be calculated based on this particular formula here. So we need to take the square root of the summation of these two divisions. Okay, so S for the first sample is the standard deviation squared, so it's the variance, divided by the number of samples that we have within our sample for that first sample. And then equally for the second one, this 2 here refers to the second sample. We're interested in squaring the standard deviation, so we're getting the variance, and then we're dividing it by the number of sample points that we have in that second sample. Okay, so this accounts for the level of difference we would expect to happen by chance when taking random samples. So that's essentially the math that we'll be using to calculate this. I hope it wasn't too complicated. You've got it all there to look at, so we'll be able to calculate that in the lab. What we're essentially doing is we're dividing the magnitude of the actual or the observed difference in those samples which we've gone out and collected, which we use here as the numerator, by the magnitude of the expected difference of the sampling means that could just happen at random, by chance, okay? So if the difference between the samples is larger, the test statistic will be larger, and that it would be more likely that they've come from different populations, okay? So there's a pretty key example within the book that I want you to look at. So that's page 161. And on there you have this, it's actually multiple pages. You have this example which focuses on female labour participation in the workforce. I think they're actually taking data from the World Bank World Development Report, which is pretty cool. So the World Bank every year produces a World Development Report which focuses on different issues each year. So I think in 2012 it was focusing on gender equality and development. What's interesting is 2021 was launched this week, and that was on data for the public good, which was exciting because they actually used some of my work within that. So I was very excited about that. You know, when I was at a university like you are, I distinctly remember in my master's course being made to read the World Development Report, and I think it was 2007 or 2008 when it was on economic geography. And it was really quite intimidating to have to read that whole document because it's pretty sizable and it can be quite complex material. So, you know, for me, it was actually really exciting that they used some of my work this year for that because it's quite a major report. Okay, so without much further ado, you know, the important rate here is that female labour participation, unfortunately, isn't as high as we would like it to be in many countries around the world. And, you know, that's a travesty for multiple reasons, particularly if you don't have full participation by certain groups, whether it's based on gender or race or whatever, then you're literally missing out substantial portions of your talent pool. Okay, so if you're interested in creating jobs, new businesses like we are, adding new value to the economy, paying tax, then you need to make sure that you're really utilising all of your talent base. And that's one of the main concerning things about you know, the fact that we have underrepresentation by certain groups in the workforce. Okay, so I need you to read this example. What's nice here is we're focusing on the different rates between less developed and more developed countries. I think that's kind of the way that people think about these things kind of historically, but I much prefer kind of higher income versus low income thinking, because developed is kind of a loaded term because that's somewhat subjective based on a variety of factors, where income level is actually very, very clear. And it does very much affect, you know, your purchasing power and your long-term health and your life expectancy and things like this. So that's just my own 2 cents on issues relating to some of the terms in the book. But in this particular example, what we're doing is we just want to examine a case where we can run these calculations for the 2-sample difference of means test, okay? So what we've got in here, if you look at the 2009 statistics in the example here, and actually I've given you all of the data, so you don't need to worry too much about it. Essentially what we have are the samples here for our more developed countries, so 15 here, or less developed and lower income countries, 45 here. And then we also have the means, so this should be X bar, so we've got the means for the two different samples, the standard deviation, and then obviously the square of the standard deviation is just the variance. So we know all of these metrics, we've done them many times before, it's really easy to understand. Now we just need to kind of piece them together, okay? So don't get scared by the big equations. I'm going to run through this fairly easily for you, and I've actually also just thrown in for a lot of these like a little Excel spreadsheet where, you know, if you want an additional way to do these calculations, you can run it through an Excel spreadsheet if that's sort of way that you think more clearly, and then we can run it later in the R code. And it just gives you an extra way to understand how we're generating these numbers, okay? So in this particular case, we need to define our hypothesis. So in the null hypothesis example, basically we're saying that there's no difference in the workforce participation rate of females between lower income countries and higher income countries. And then the alternative hypothesis is essentially that there is a significant difference in labour force participation rates for females between low income and high income countries. But what we're not saying is any direction as to which way that runs. Okay, so you'll notice here that this is a two-tailed test. Hopefully you understand that now from the work that we did in the previous sessions. And essentially what we're saying is it differs. We don't know which way that direction runs, but we just think it's going to be significantly different in some sort of way. Okay, so we know the test that we're going to run because we're focusing on that right now. And we're going to calculate the test statistic. Okay, so we've got a relatively small sample size here, so less than 30, which means we're going to be using our t-distribution, which means we're going to be using the t-test. What we need to do is we need to run through those equations that we have from the previous slide. So we covered it. We need to basically get the standard error of the difference of the means first. And then essentially we need to, once we get that number, 3.8, we need to input it in. So our equation here is the denominator, and then we need to take our difference of the means as the numerator, okay? So I think it should be fairly straightforward for you to kind of follow this through. So for the two samples that we've got, N1 and N2, we know that we have 15 and we have 45 samples depending on those two. So we can plug them in here, N1 as 15 and N2 as 45. So you can see them just here on the right-hand side. And then what we need to do is we need to get the standard deviation. So that's 7.82 for sample 1 and 16.5 for sample 2. So we can then plug those in. They need to be converted to the variance, so we need to square them. But then once we've got that, we're able to basically take those divisions, sum them, then take the square root, and we get 3.18, which is basically our standard error of the difference of the means. Okay, so this value here. And then once we've got that, we can then move on to actually using the mean value. So we know for x1 we've got 52.6, and for x2 we've got 51.2. And essentially we're able to place these into the numerator part. So these are percentage participation rates for females in the workforce. And essentially then when we take that subtraction and we divide it by the standard error of the difference of the means, then we get 0.44, okay? So that 0.44 is standard deviations above the mean. That's the t value, the t statistic that we get. That indicates a significance value of 0.65. So remember that in pretty much all of our significance testing work, we're going to be using a significant alpha value of 0.05. That's our significance level. And the reason why we do that is because then we can be 95% certain that the results didn't just occur by chance, okay? That means that that 5% refers to that 0.05 portion that we expect. So it's only significant if the t statistic is within that part of the distribution where those 5% of the values lie either above or below the mean, depending on the type of the hypothesis that we test. Okay, so for those astute of you who've noticed 0.65 is far above that significance level of 0.05. So as a consequence, we do not have enough evidence to actually reject the null hypothesis. Okay, so we basically find that those means could certainly have just occurred by random. We don't have strong enough evidence to reject the null and accept the alternative hypothesis. So we basically stick with the status quo, which is that there's no difference here. And I think that generally follows kind of our existing a priori thinking, so our prior thinking on this topic, which is that essentially female participation in the workforce is multifaceted. There are multivariate reasons for why that may be higher or lower. Very often it's down to cultural factors, and as a consequence, you can look at the book the map which is in there, and you'll see that that rate really differs quite a bit across different countries. So there's quite a large amount of cultural difference which is influencing the variation of that rate. Okay, so it doesn't really strictly relate to income levels as we've kind of demonstrated here, because we don't have any conclusive evidence. Okay, great. So if you want to stick these numbers into the Excel spreadsheet, you can do, and you can calculate the t-value just so that you know how to do this manually. The issue, of course, is that for this data here, we've been just pretty much assuming that the data is normally distributed. We don't always know that. And actually, it's pretty good to formally test that. But I think the key point is that we have issues. Well done for checking, thinking about whether we meet the assumptions or not. That's how I want you to think about these statistical tests. But as I say, maybe the data aren't normally distributed, or maybe the data we have are only ordinal or ranked, and therefore we may need to think about a non-parametric approach that we could use to actually make some sort of statistical analysis of the data that we've got. Okay, so one way to do that would be to use the Wilcoxon rank sum test. That's one of the most widely used, but we could also use the Mann-Whitney U-test. Okay, so we're going to focus on the former now. So the Wilcoxon rank sum test. So this is just a continuation of the previous example, but we're going to think of it in terms of the fact that the data are not normally distributed. So before we begin, the objective is to compare those two independent samples to see if there's a difference between them. We have, as I mentioned before, every week, these requirements, which are essentially the assumptions for meeting this statistical test. So we need to have independent random samples. The populations have the same shape of a non-parametric distribution. And the data, in this case, are ordinal. So that means that they're categorical, but we have some sort of inherent hierarchy, so that enables us to rank them. So that's really the key kind of word here, because when you think about the name, so Wilcoxon was the person who invented the test, then the rank sum is what we're going to do. We're going to rank all of those data points, and we're going to sum them up to get that value. And we'll do that within R later. So before we get there, the hypothesis for the null would be that there's no difference in the rank sums between the two populations. The alternative hypothesis would be that there is a difference in the rank sums between the two populations. Or if we wanted a directional hypothesis, we could say that the first population is larger than those of the second population, or vice versa. Okay, and the test statistic which we're looking for here is this ZW value, so the Wilcoxon value. What we want to do is we want to get that test statistic here, but we need to basically take the sum of the ranks of the sample, and we need to subtract the mean of the ranks of the WI of that sample, and then we need to divide it by the standard deviation of W. Okay, so it's a fairly straightforward equation. Just to get that mean ranks value here, you need to take the number of samples that you've got multiplied by the number of samples in sample 1, the number of samples in sample 2, plus 1, and that's the numerator divided by 2. Okay, so I appreciate me just talking through these equations isn't necessarily the easiest way for you to get a hang of this, but I just want to emphasize that this is all really kind of straightforward data. We just need to recognize that we need the first sample here for the number of samples, and the second sample here for the for the number of samples. And when we plug it in, we're able to basically obtain all of the inputs that we need for this very, very simple equation here in order to get our test statistic of ZW. So what are the steps in this Wilcoxon test? Well, firstly, we need to actually combine these samples together into a single data set. We need to then order and rank all of the sample data from the smallest to the largest. Okay, and when we have data rows that basically are tied, then what we do is we assign the average rank value to each of them. We then need to sum all of those ranks for sample 1 and sample 2 respectively. So we get the sums W1 and W2. And then we need to get the test statistic. Okay, so we know how to do that from the previous example. Finally, then we can test with that test statistic what the p-value is, and we're generally looking for something that's below 0.05 if we want to be 95% confident in our results, and we only want a 5% error rate. And then we make a decision about whether we accept whether we retain the null hypothesis or whether we have enough information to reject the null hypothesis and accept the alternative hypothesis. Great. So let's go back to our example from before. So the question is, does the involvement of women in the labour force vary by the economic development of different countries? So we have the way to obtain the test statistic up here in the top right hand corner. We want to obtain this ZW test statistic, okay? So we have the lower income groups here where we have 30 in the sample. We have a W1 value of 746.5. And then we have the same for the higher income group, but we only have 14 sample data points, so it's quite small. We're going to need to use a t-test, the t-distribution, because it's under 30. And we've got a W2 value of 243.5, okay? So what we're going to do is to get this ZW value down here using that very simple equation. And what we can do to get the W2 value here, which is 243, well, that's simple. We can just input that straight into our equation. But we need to get this W bar for the second sample, which means we need to run through this particular equation here. Okay, so the W bar is the mean ranks of W. So we need to take the sample size for our sample, which is 14. We need to take the sample size for sample 1, which is 30. So we've got 14, 30, 14 again, as we want the sample size for sample 2. And then we can work through all of those components to get 315, okay? So that gets us all of our numerator components just here. And then finally, what we need to do is we need to obtain the denominator here, which is the SW value. So you need to work through this equation here. It looks more scary than you think it is because it's just reiterating the previous slide equation, but this time we're inputting all of those values in, and we get 39.69. So we can then actually finish this and obtain the test statistic of minus 1.805, and that's standard deviations below the mean. And when we actually get the p-value for that particular test statistic that we get a p-value of 0.071. It's two-tailed, it's not below 0.05, and therefore we do not have a significant result. So we do not have enough evidence to reject the null hypothesis and accept the alternative hypothesis. So we just retain the null hypothesis as the standard way of thinking about the world on this particular issue. So we're essentially saying that there's no effect, there's no a relationship between the economic development of a country and the level of participation of females in the labour workforce. Okay, so hopefully that's kind of quite clear to you. As I say, please read page 166 in the book and work through those examples, and then you should have a fairly clear understanding of how to actually get those test statistics. You may, in other circumstances, have proportions that you need to actually obtain. So if that's the case, maybe you have outcome binary variables. So let's think of the number of people who answered yes or no to a question which we asked about student satisfaction. And essentially what we did was we then wanted to get the proportion of people who had one lecturer and then actually compare it to the proportion of people who had a separate lecturer, and then understand if there were differences in the proportions of those responses. Okay. So let's think through those requirements, those assumptions. We need independent random samples here, and we need the outcome variable to be binary. We know that this row value for the null hypothesis is basically assumed to be the same in each of those samples. And then the alternative hypothesis, obviously, is that we expect that they're different. So they're significantly different, and therefore they're from different populations. And then that's obviously a two-tailed hypothesis test. You could also have this one-tailed hypothesis test if you kind of had an a priori understanding of whether you think that one proportion would be higher or lower than another. So maybe you had the student satisfaction surveys for one particular lecturer from a previous year, and as a consequence, you kind of had an idea as to whether they were going to be better or worse than another another lecturer who had been given a set of classes to a group of students at GMU. So you could use that information to basically direct the hypothesis test that you want to make. Okay, great. So we're interested in this p-value as the test statistic. And to get this particular test statistic, we need to basically find the difference of proportions between the two samples. So it's basically subtracting this p2 from this p1. And then what we need to do is need to divide by the standard error of the difference of the proportions, and I give you the equation down here. The only curveball that I've thrown in there is the p hat. So you can see this little well, it's called a hat, this little squiggle on top of the p. You can calculate that by using this lower equation here. So it's not actually complicated math, it's just lots of components. But if you know the sample size for sample 1, the proportion for sample 1, and the sample size for sample 2, and the proportion for sample 2, then you can calculate this really easily, okay? And I think we've been through plenty of these examples now. You just need to work through the math and get that test statistic for this particular test. Great, so I hope that that's going swimmingly for you. Now we've kind of passed the first part of this lecture, and we can get stuck into the second part of the lecture. You remember in the first part, we were talking about independent samples. So I told you I wanted you to go out and get house prices from Fairfax. And then I told you I wanted you to go drive down to Richmond, and I wanted you to do a house survey there and get the house prices for Richmond, Virginia. Imagine that we didn't have those types of independent samples. I just said to you, I want you to sample house prices in Virginia with a 1-year time difference, and in that period maybe we've had like a major economic hit. So maybe we've had COVID, maybe we had a global financial crisis, and that may affect the number of house prices. Sorry, the actual house prices as a result of, people maybe losing their jobs very sadly, not being able to pay their mortgages, and therefore there being more houses in the market, and that supply bringing down the price, partly also because there's lower demand. So I think that's fairly straightforward. This is just basically picking up the things that I mentioned about before. But I think what's really nice about this is you kind of want to be able to test interventions. Okay, so at that diagram I showed you at the beginning, and I've shown you it through the class, the whole semester. Why are we here? We're here to make the world a better place. What enables that? Well, making better decisions. So does a government policy work? Does a business practice for a large corporate that you work for actually work? Does it improve revenues? Does it improve customer satisfaction? Does it improve society? On the government side, they'd be thinking, are we improving the outcomes for our citizens? Are more people having access to basic services? Are their life chances improving? When you've got this type of matched pairs example, you can actually test if you have data before that intervention and data after that intervention. You can test the effectiveness of that particular change that's taking place. And therefore, it's really nice. It's a really nice way to get data before an event, and then kind of rigorously statistically demonstrate that something did or didn't work. I suspect actually quite a lot of policies might not work at the government level, and therefore this is really kind of important information to actually understand. So how do we get there? So basically we need the objective. So let's say we want to compare the matched pairs for Fairfax house prices before and after major events. We have a set of assumptions, so we know that because it's parametric, this particular approach, we're going to need a random sample. We're going to need paired data, so that's a single entity, so a single house before the actual intervention and the same house after the intervention. Okay, and we want the house price for that one single entity. We assume that the populations are normally distributed because this is a parametric test, Gaussian-based approach. And because we're focusing on continuous means here, we need the data to be in this kind of interval ratio data type state. So the hypothesis here, we're interested in delta. So delta is always the measure of change in math. So if you did physics, for example, remember that delta often refers maybe to the change in the speed of a vehicle, for example. Here we've got lowercase delta referring to our hypothesis. So in the null hypothesis example, basically delta is equal to 0. So what we're saying is that there's no difference between the before and the after data that we obtained for those entities that we surveyed. And then the alternative hypothesis obviously is that there is a significant difference. And then that could be, that's two-tailed there, we don't really specify the direction, or we could specifically specify the direction if we had some a priori knowledge about the size of the effect that we think. So you know that Fairfax is doing reasonably well, it's close to DC, so you could have an expectation that the house prices there, you know, potentially might be more resilient than if we looked elsewhere. So it might even be that the house prices have increased over the last year rather than decreased, which actually I think they actually have. So anyway, that gives you the ability to specify your hypothesis. And then we want the test statistic. You know, that's exactly what we're going for in these tests. That's the statistic that we want to calculate. And actually, it's pretty easy down here for this particular approach. So the TMP, which is the test statistic here, we need the D bar. So D here refers to the differences. So what we want is the mean of the matched pairs difference. So it's the mean because we've got the bar over the D here. And it's D because we're focusing on the differences between the pairs. Okay, so it's actually quite easy to calculate this. We just need to subtract. So imagine we have entity I. We need the data point for X, which could have been a year ago, and the data point for Y, which is this year. We need to subtract them to get the differences. Then we need to sum them all up and divide them by the number of data points that we have. And this is how we get the mean value of the matched pairs differences, okay? So it sounds really complicated, but it's not. It's just literally finding the mean difference across all of those pair combinations that we've got. I mean, it's that classic statistics thing of where the language just is so alien and abstract. By the time you actually see the math for the equation, you think that it's almost deceptively more complicated than it needs to be. Okay, and then we need to get this standard error of the mean difference at the bottom down here. So this is a bit more complicated, but basically we just need the standard deviation of the matched pairs differences. Fine. I mean, you've calculated the standard deviation plenty of times, so we're getting the differences from the mean. We're getting the sum of the squares of them, and then we're dividing it by the number of sample points times by the number of degrees of freedom, okay? And that gives us our standard error of the mean difference. Okay? So this one isn't actually in the book anymore, but it's from a previous version of the book, but I kind of like it, so we're keeping it. And it's a good example because, I mean, the question is, does historical temperature show an increasing trend in the United States? And this is for places sampled at weather stations in the American Corn Belt. Okay, so we have the average annual temperature for 28 weather stations in the American Corn Belt, and we have the data basically for the mid-1970s, so a really long time ago, and then the mid-90s, which is a long time ago for you, but you know, this is the period when I grew up. So that's great, and then we basically have all of those data points down here. So these are listed in annual degrees, average annual degrees in Celsius. and then we have the same for the 1970s period here. So the point is, it's not in Fahrenheit, it's in Celsius, and that's because most science is carried out in metric, not imperial units. And then the point is, we get that x and that y. Okay, so you remember here we're looking for the xi and the yi in order to get the differences for one single matched pair. Well, here we go. If you've got Cairo, we have the 14.5 for the most recent value, and we have the 15.2 for the previous value, and that's our matched pair. Okay, so we can get that d value, the difference, by subtracting one from the other. And if we do that, we get minus 0.7 for that first row. And then you'll notice this rank over here, and this is really the crux of this analysis part. We're focusing just on the matched pairs at the moment, but this is going to be more important as we start to move on through the tests. So test statistics here. What we're going to do is we're going to try and find the test statistic of interest. So we know our hypotheses. So if D is equal to 0, then there's the null hypothesis. But if we think that the alternative hypothesis is that the difference is, so the temperature is larger than 0. So we think there's a positive effect, and it's a one-tailed approach. We have all of the test statistics here. What we want to do, as I mentioned before, was to find this TMP test statistic. So we need to get the D bar and the standard error of the mean of the differences. So to get the D bar here, we just need to sum up those DI values, divide them by the number of samples. So we get the sum of D, which is 5.5. We get the number of samples that we've got, which is n equals 28. So that's 1.96, which is the product of this this equation just here. And then what we need to do is need to get the SD value, so this standard error of the mean difference. So we just need to run it through this particular equation here. So there's a slight difference in how the equations have been calculated here. So we just use the number of degrees of freedom as the denominator here. But don't worry, because we still introduce the sample size over here again. I don't know why in the book they calculated it in 2 different steps, but I just wanted to point out that that denominator works. It's just being done in 2 different steps here, okay? But the point is that we end up with 2.07, and when we get that, what that essentially means is our p-value is below that golden significance level that we want, okay? So if we want to be 95% certain that the results haven't just occurred by chance, then we need a significance alpha value of 0.05. Now p-value here is below that. So we do have a significant finding with 27 degrees of freedom, which as a consequence means that we have enough evidence at the 95% significance level to reject the null hypothesis and accept the alternative hypothesis. Okay? Fab. Hopefully that's not too confusing for you. What happens if my data do not conform to these assumptions? So if the data are ordinal, for example, or if the sample sizes are too small for parametric approaches, that's fair enough. Or more importantly, in my own experience, if the data are not actually drawn from a normally distributed population. So the Wilcoxon-signed rank sum test is the non-parametric equivalent for dependent samples match pair problem. So let me just repeat that. The Wilcoxon-signed rank test is the non-parametric alternative, okay? So what do we do in order to obtain the test statistic for this particular approach? So we know the objective is that we're comparing the matched pairs for those differences. We need a random sample, we need paired data because we're focusing on those paired tests right now. So we don't have independent data, that the data are dependent across those 2 samples. We're actually assuming that the populations don't have normal distributions here. So I think that's a mistake in the slide that I just need to change. And then we're assuming that the data are ordinal, okay? So that there is interval ratio data here that we actually transformed into ordinal form. Okay, so these are categories, but with some inherent ordering based on their magnitude. So the hypothesis is that there's no difference in the ranked matched pairs. The alternative hypothesis obviously is that there is some difference, but we just don't specify which direction. We don't know if it's higher, we don't know if it's lower. And then obviously we could have a more directional hypothesis if we wanted to, if we had some a priori knowledge of which way the magnitude may run. Okay, so whether we think that this particular outcome might be higher or lower based on our pre-existing knowledge. And then we need to get the test statistic ZW here. Okay, and this is the rather intimidating looking equation, but it's fine. We're going to run through how we get that. So in the lab, we'll run through this, but basically what we do is we get the matched pairs differences and we rank them from the lowest to the highest, and we get the absolute difference between the two variables to determine the rank. And when the difference is 0, we ignore them in the ranking, those particular rows. And when the differences are tied for a particular rank, the mean rank is allocated. Okay, so these are just some fairly standard steps that we need to take in order to conform to that particular statistical test that we want to actually use. The trick is going to be working out which t-value to use. So essentially the matched pairs differences are ranked, as I've already mentioned, from the lowest to the highest. The sums of the ranks for positive differences is TP, the sums of the ranks for negative differences is TN, and then we need to make a decision as to which parameter we use. So the alternative hypothesis, one-tailed, use the T with the smallest number of differences, or if we have two-tailed alternative hypothesis, we use the smaller of the TP and the TN. Okay, but you kind of get quite similar results either way, but we have these kind of formalized rules, and I just wanted to make you aware of them because it's good to kind of know exactly how to use this test. So there's an example if you want to follow this within the book on page 172 of McGrew et al. What I've done here is I've actually just placed the data into a very simple table, and you're able just to recreate this in Excel if you want to. This just gives you, another way to understand how these data are actually arrived at. So you could have these as a data frame in R, or you could store these as arrays for each variable. But essentially, what we want to do is we want to get the X bar value. So that's for this, this particular column here. So this question's focusing on the daily indoor water usage before and after a water reduction program. So we have the before number of gallons consumed. I said we always use a metric in scientific experiments, but actually here we've got imperial. But then again, the book actually switches between imperial and metric units quite regularly. And then after the water intervention that we carried out, we have an amount of water that's being consumed by our households. So we know that consuming water in the house is an important factor in kind of reducing our environmental impact. So when we use fresh water, there's a carbon impact to that because we require energy to process water in order to make it clean for us to drink, cook with, use anywhere else in the house, have a shower, etc. And therefore actually is very beneficial for the environment if we reduce our impact by using less water. So that's why these water reduction programs are actually really handy. I think particularly in the future this is more and more important because we know that we're going to be moving towards drought conditions in some parts of the world as a result of a changing climate. So this is going to become a really pertinent issue. So we've got the before and we've got the after for 11 households. So this is the household ID here. So we've got a very small sample. So we'll be using a t-distribution and t-test. We're able to get the change. So we get the change between the x and the y. And essentially what we then need to do is we need to rank from the smallest to the largest. Okay, so the smallest change here is 1.8, so it gets the rank of 1. The second largest change is minus 4.9, so that gets 2. So on and so forth, all the way down through all of the different change values that we've got, all the way to the bottom rank, which is rank 11, where the change is minus 27.5, so it's the largest difference. And essentially we can get the X bar value, which is just the mean for this particular column here, or the y bar value, which is the mean for this column. I've just placed the formulae for the Excel spreadsheet here if you want to run it through yourself. And then for the Tn, what we need to do is sum based on whether the value is below 0, or for the TP whether it's above 0. Okay, so we end up with these two different numbers depending on whether the values are above or below. Okay. So, does a water reduction campaign reduce water consumption? And the key part in this question here is reduce, because it means that we're going to be expecting for there to be a reduction in consumption, and therefore we're using a one-sided, one-tailed test. We're going to use the Wilcoxon match signs ranks test because we know that this is non-parametric data, and we want to be able to compare before and after this intervention. We have our sample statistics for Tn and for Tp, and the overall number of samples that we've got, which is 11. And we have a hypothesis, so we expect there's no difference in the null hypothesis case, but then we expect the alternative hypothesis to actually be a negative difference. And therefore, because we're expecting this, we're going to use the TP value, okay? So remember, we selected T, which corresponds to the smaller number of hypothesized changes, and TP is the smallest. So the test statistics, how do we get that? Well, we need to basically run through this equation down here. We've determined what T we're going to use. We've got the size of the sample, which is 11. And then we've also got all of these other values that we need to fill out. And when we run through that, we get this test statistic of minus 1.245 standard deviations below the mean, okay? So as a consequence, that means we get a p-value of 0.1, which isn't below the 0.05 significance level that we're going to be looking for, which means that we don't have enough evidence to reject the null hypothesis. So that's pretty clear that there wasn't a significant reduction in the water consumed. The result could just have occurred by chance. And as a consequence, we can't accept that, that the water reduction campaign had any significant impact. And I think that that's a fairly important tool to learn, because if you think how much money we spend on interventions like this, we need to make sure that we're spending the money in a clever way, in a resourceful way, in a way that maximizes, for example, in this case, probably taxpayer dollars, so that the maximum bang for each buck is achieved. And as a consequence, we need to make sure we have good policies, and this is a way for you to be able to directly evaluate some of those policies, okay? So, that's it for today. That's the lecture. Thanks for hanging with me. I appreciate we've covered quite a lot. So we covered, there's two different parametric tests within independent samples. And then we also cover the non-parametric test for the independent samples, so Wilcoxon rank. And then for the dependent matched pairs, at the end here, we covered the matched pairs t-test if you've got normally distributed data, and the Wilcoxon matched pairs signed ranks test if you've got non-parametric data. Okay. Great, well, thanks a lot for tuning in, and I'll look forward to seeing you in the lab, and please do reach out to me if you've got any further questions. So, thank you, goodbye.